Hello and welcome to Knowledge Review number 7 for the Object-Oriented Programming 2 section. Alright, here we are at the very end. The interesting thing is this Knowledge Review will be very different from all of the Knowledge Reviews that you've experienced so far. In the past, all Knowledge Reviews consist of a single video. In that video, you are presented with a challenge and then asked to pause the video. Try the challenge on your own, and then come back and compare your results with ours. This time around, the Knowledge Review is going to be broke up over multiple videos due to the complexity of the application we are going to ask you to write. Complexity? That's right. You have learned a great deal of the C# language. You have now learned a great deal of how object-oriented behavior works. Now it is time for you to merge these two things together and begin planning more complicated applications. This is important. You are not always going to be creating one-page programs for the rest of your life. I can prove it. Here in the XNA 101 class, as you progress from precision into the more complicated games that we have lined up, the code base will get larger and larger. There's just going to be more and more code that you're going to be dealing with. And due to that, you really have to get an understanding of working with larger applications. Not that this particular application is going to be a larger program, but the logic in it is going to get a little bit deeper, and the scope of the application itself is larger compared to all other knowledge reviews that you have done so far. Now, you are responsible for understanding everything from Volume 1 all the way up to right now. That is a lot of material. Feel free to go back and review the Hyperion project, because now, if you go back and watch it, you're going to find yourself extremely comfortable with everything that we present in there, with perhaps the exception of arrays, but even then on the whiteboard we explained how the arrays worked. So, with an understanding that everything is fair game from all the way back in Volume 1 all the way up to right now, there's a lot of different techniques that you can apply to the application that we are going to ask you to write. Now, because this application is a bit sophisticated, this video is only going to present the challenge. Then we'll have multiple videos that will start off by giving you hints as to how you could go about accomplishing a particular task, and then asking you to pause the video in case you did not go in that route, and then start the video back, and we'll show you how we accomplish that particular part of the application. So this should be a very interesting experience for everyone. So what are we asking you to create? Well, we're going to be asking you to create a directed acyclic graph and a command line interface. Okay, right now I've probably lost 95% of all of our beginners. Wouldn't you agree, Logan?
Yeah, everyone's like, wait, what?
Exactly. So let's go ahead and pull up some sort of whiteboard to start explaining.
Repeat the last two things you just said.
That's right. So first of all, you will be creating the following. Let me go ahead and pull out a pen here. A directed acyclic graph, just commonly referred to as a DAG. You will also be creating a command line interface. Both of these, of course, will be wrapped up in a single application. Now, please keep the following in mind. This application will require some forethought. You will need to sit down with paper and pen and plan it before you begin coding. If you just jump into Visual Studio and start trying to code this out, you will probably run yourself into a logic corner. This is where it's very difficult to work your way back out. You will become frustrated and, well, perhaps just quit. Please, I beg of you to try this challenge. Try to work your way through it, because you do know everything language-wise required to pull this off. Okay? Now, what exactly is a directed acyclic graph? It's simply a directed graph that cannot cycle. What do I mean by that? Well, let's start talking about nodes. A node is going to be a basic building block. Nodes can represent anything, but we're going to basically represent nodes the same way that some 3D applications represent nodes. Building blocks that will contain particular types of information. So this is a node. Let's bring another node into the picture. So here's another node. By connecting this node to this node, I have just created a hierarchy. So my graph right now contains node 1 and node 2. Since this is a DAG, or a directed acyclic graph, node 2 cannot become the parent of node 1. Okay? In fact, let me go ahead and get that term out of the way real quick. Parent, child. Very important to understand. Okay? Now, of course, this child may have a child of its own. The bottom line is, when you're dealing with a directed acyclic graph, you end up with the following scenario. You can say the path to go from point A to point B, when we're at point B, there should be no way for you to get back to A. That's the idea. And if you take a look at the graph we've drawn out right here, as we work our way from node 1 down to node 3, once at node 3, how could we get back to node 1? There is no way to get back to node 1. So that is the idea. You cannot have a cyclic condition. Okay? So where are directed acyclic graphs used? What I'm going to do is bring up an application, a good friend of mine, known as Maya. Now Maya makes use of two types of graphs. We have the DAG and we have the dependency graph. We're going to ask you to write the DAG that is very, very similar to Maya. Now, don't panic. It's not as sophisticated as you're probably thinking it is. Now, if you've never seen Maya before, you can head over to Autodesk.com and search around for their PLE, the Personal Learning Edition, download it, and follow along with the little example I'm about to give you if you're interested in checking this out. Now, I'm just using this for, or as, a visual aid only. Let's go ahead and come in here and create something. Let us create a sphere. So if I come over here and draw out a sphere, that's funny, actually giving me a hard time using the pen. Let's delete that and use a mouse, a real mouse. So I come over here and draw out a sphere. There we go. I have just created some nodes, remember? Basic building blocks. Now I'm going to move this sphere out of the way. So I'll just kind of move them over here. Now, let's come up here and create another sphere. So I have created two pieces of geometry. And I'll move this one over here. Now what I am most interested in is the hypergraph. It is a window utility inside of Maya that will allow you to see your scene graph. So let us go ahead and come up here to Window, and I'm going to come down here to the hypergraph, and I'm going to view the hierarchy. Remember, in Maya, we have two types of graphs. We've got the directed acyclic graph, the DAG, and we have got the dependency graph, the DG. The DAG is our scene graph, our hierarchy. So that's why I'm coming in here to hypergraph hierarchy. So I'll click on this. We have got two nodes. These are transform nodes, and transform nodes contain transformation information. Translation data, rotation data, scale data, etc. Each of these nodes represent where the object is going to appear in the world. So as I select an object, you'll notice that that particular node lit up yellow. So I select this node by dragging over it, this one lights up yellow. As I move the object around in 3D space, you'll notice the data is changing over here. So move it up a little bit, the data has changed. Alright, good enough. So we've got two nodes. Now, these nodes actually have another node associated with them. Right now, what we are looking at are transform nodes. So let's go ahead and jump back over to the whiteboard real quick. We're looking at transform nodes. So here's some terminology. Okay, that's the worst line I've ever seen. Let's draw that one more time. Ooh, that's much better. All right, first of all, transform node. Transforms node's primary job, as far as you are concerned, is to say where in the 3D world something will be. Period. Now, I'm going to introduce you to a shape node. A shape node contains the meat of the object you're dealing with. Let me show you what I mean. If we jump back over here into Maya, our shape node, in the case of geometry here, our two spheres, would be the actual geometry itself. All of the CVs or vertices that make up that particular piece of geometry. So over here, you'll notice all I see are transform nodes. Let me go ahead and zoom in by holding Alt and the left and middle mouse button. Of course, I can use my scroll wheel as well. And let's go ahead and hold Alt and the middle mouse button to move over. There we go. So NURB Sphere 1, NURB Sphere 2, both of these are transform nodes. As I select them, I'm looking at transformation information. Now, a shape node is going to, in the case of geometry, contain just geometry information. It doesn't dictate where the geometry is going to be in the world. That is the job of the transform node. So we have how many shape nodes in the scene right now? We should have 2 because we have 2 pieces of geometry. Each shape node is going to have an associated transform node. And the associated transform node dictates where that geometry is displayed in the world. I can prove this by coming up here to Options in the hypergraph, come down to Display, and then come across to Shape Nodes. Let's turn it on. You'll see that by default, our shape nodes are hidden. So now we can see that we have a transform node named NURBS Sphere 1, a transform node named NURBS Sphere 2. Associated with each of these nodes is the shape node. Here, by selecting on it first, you'll notice we've lost all of our transformation information. That's right, because inside this shape node, we have our geometry representing the sphere that you see in the viewport. This guy is linked to the transform node. So wherever the transform node moves around to, that is where you're going to find your geometry. Same thing over here. Anywhere we move NURBS Sphere 2 around to, and again, that's a transform node, the shape node is going to be in that particular location. So you can see it's the transform nodes that basically say where the geometry is going to reside in your 3D world. Shape nodes cannot exist without a transform node. Okay, that's just a rule we're setting down right now. So I'm going to come back up here to Options, come back to Display, and turn shape nodes off. So we all know that as I come in here and I create geometry, I get a transform node and I get a shape node. By default, we cannot see that shape node, it's hidden. So you can think of our transform nodes as simply representing the objects that we see on the viewport. Deselect, select, and the transform node lights up yellow, indicating that the object has been selected. Alright, well this is all great and, good fun with Maya, but where are we going with this? Well, again, we are right now working inside of a scene hierarchy. And right now we see that we have 2 objects at the scene root level. Let's go ahead and add one more sphere by coming up to Create, NURBS Primitives, Sphere. We'll draw this guy out. And now we have 3. Let's go ahead and just maximize this so that everybody can focus on what I'm getting at here. So we have 3 transform nodes. Each of these nodes is representing a sphere in the scene. Each of these nodes also has an associated shape node. And there's all 3 shape nodes. Now, let us start creating hierarchies. Just like we were creating hierarchies with inheritance back in C#, we can create hierarchies here, but hierarchies in this 3D world are going to act very different in one sense from the hierarchies that you were creating back over in the C# world, because now we're dealing with something you can actually see. Okay, it's a little bit different. Check this out. I can take NURB Sphere 2 and make it a child by middle click and dragging and dropping on NURB Sphere 1. So NURB Sphere 2 is now a child of NURB Sphere 1. So this is our parent, this is our child. NURB Sphere 1 is said to be at the scene's root. NURB Sphere 3 is at the scene's root. If I grab NURB Sphere 3, middle click and drag him over to NURB Sphere 1, now we can say that NURB Sphere 2 and 3 are children of NURB Sphere 1. Okay? If I was to middle click and drag NURB Sphere 3 onto NURB Sphere 2 and let go, we could now say that NURB Sphere 3 is a child of NURB Sphere 2. So let us go ahead and see what happens back in our viewport. So let's go ahead and Alt and left and middle, and then I'm going to go ahead and just Alt middle, move this over, Alt left to rotate it around, just in case you are completely new to working with Maya. And then let's just Alt and middle mouse button to center that up. Alright, let's select NURB Sphere 1. By selecting NURB Sphere 1, the root of this hierarchy, everybody just changed colors. Everybody lit up green. This is indicating that if I was to move the object around, that all of the objects will move. If I was to hit the rotate key, I'm going to hit E on my keyboard, and rotate, notice that all objects are rotating. If I was to, I'm going to hit the minus key just to shrink that down a little bit, rotate around the y-axis, you'll notice that my parent sphere, NURB Sphere 1, is acting as the center of the universe for the other 2 pieces of geometry, the other 2 children. Now in this particular case, NURB Sphere 3 is more of a grandchild of NURB Sphere 1 because it's not a direct child. What's happening here is NURB Sphere 1 rotates, causing NURB Sphere 2 to rotate because it comes along because it is parented. But as NURB Sphere 2 rotates, that's forcing NURB Sphere 3 to rotate. So if I was to select NURB Sphere 2 and rotate it, check that out. NURB Sphere 1 is no longer highlighted green and is not moving. NURB Sphere 3 is still moving along. So I can kind of rotate this around, hit W to grab my move tool, and then go ahead and pull this on back and push it down a little bit. Okay, so there we go. Of course, if I grab NURB Sphere 3, he moves on his own. It does not affect anyone else. He's at the end of the hierarchy. Logan, is there anything you'd like to add into all this?
Nothing I can think of. I mean, it's just a simple, but it's a hierarchical system so that things can be organized together and basically have transformations controlled in a hierarchical manner.
That's right.
Meaning one can select at the root of a hierarchy and cause transformations to propagate throughout the entire hierarchy.
That's right.
Or to be able to drop down into sub-pieces of that hierarchy, sub-branches, and move only those. So the idea is that we have transform nodes. Each individual transform node is used to represent position, but we have the additional ability to parent these nodes together such that any children will receive information from their parent. So that, and there's another example of directed information. Any child receives information from its parent, but parents do not receive information from their children. You move the children around, and the parents stay where they're at. So it's a way of controlling transformations on a hierarchical level, to have transformation take place from the root and be propagated down, or to take place from only from a specific branch down, or even the final child where no other transformation is applied except to that one child.
Exactly. Let's go ahead and create something else. Let us create a light. So I'm going to come in here and create a point light to illuminate our scene. let's take a look at what is going on back over in the hierarchy. So if we come over here, you'll notice, once again, what do I have? Even though it says point light, it is a transform node. Coming back up to options, display, and coming over here to shape nodes, turning it on. Everybody's got a shape node. Okay? Shape nodes, right? My bad. Shape node, shape nodes, shape nodes, shape node. Okay? Let's go ahead and turn those back off. I just want you to see that every time I actually create an object, such as geometry or a light, it has a shape node because it's the shape node that's the meat of the object you just created. It's the transform node that dictates where that object is going to appear in the world. So let's come back up here to options, come down to display and turn shape nodes off. Alt middle mouse and move this back down. So all we have right now is a group of transform nodes. How many transform nodes do we have at the root level? 2. NURB sphere 1 and point light 1. How many children does point light 1 have? He has none. How many children does NURB sphere 1 have? Well, direct children, he's got 1. That would be NURB sphere 2. You could, of course, say, you could look at it where all of these are his children. But in reality, his immediate descendant child would be NURB sphere 2. And NURB sphere 2 has 1 child as well, NURB sphere 3. Now I can middle mouse NURB sphere 3, drag and drop over here on the point light, and you can now see that the point light, when selected, also causes NURB sphere 3 to illuminate. So now when I move this around, you can see that by moving around my point light, that once again, transformation information is flowing down to our NURB sphere 3 transform node. Okay, and because that position data is updating, the shape, the true geometry in the shape node goes along with it. Okay? So I can work with these hierarchies all day long. I could say, let's go ahead and come in here and take, every time I roll or push on this, the mouse rolls, and that's what's causing that to jump up and down, guys. But I can go ahead and select NURB sphere 1, middle mouse, drag it over here to point light 1, and now let's take a look at the hierarchy I've created. Point light 1's children would be NURB sphere 1 and 3. NURB sphere 3 has no children. NURB sphere 1 has 1 child. So I could say, point light, how many children do you have? It has 2. NURB sphere 3, how many do you have? 0. NURB sphere 1, how many do you have? I have 1. Okay? This is all very important stuff because you're going to create an application back over in C# that will mimic this scenario, nodes and all. Okay? So, Logan, at the moment, I think this is probably enough information for us to jump back over to the whiteboard and start talking a little bit about the creation of these nodes and all before we come back and start talking about the command line interface. Sound good to you?
Yeah, sounds good.
All right, so let's go ahead and jump back over here to the whiteboard. So, what will we need to be able to do? Well, there's a lot of things we need to be able to do, so I'm going to need some room here. I'm also going to need something to block these buttons on the Wacom tablet. Here we go. All right, so we've looked at some terminology. Now, must be able to do the following. Your application must be able to create transform nodes. You must be able to create spheres. No actual geometry, guys. Just a representation. Must be able to create lights. Must be able to create groups. Let's take a look at that one real quick. Jumping back over into Maya, let us go ahead and create a new sphere. And let's take NURB sphere 2, middle click and drag him to nowhere to unparent him. So he is now back up at the root. So I have got how many transform nodes at the scene root? 1, 2, 3. So 3 top-level nodes. I want to group this object and this object. So NURB sphere 4, NURB sphere 2. So I'll select both of them. So I could just select, hold shift, and grab the other one, or I could just marquee over both of them. So I have selected 2 objects. Now I'm going to come up here to edit, and I'm going to group. Watch very carefully in the hypergraph as to what happens. Boom. I got a new transform node created, and my 2 other transform nodes, the 2 transform nodes that I had selected, the 2 that represent the 2 pieces of geometry in the scene, were both just parented to this new group 1 transform node. So this group 1 guy, he is just a transform node. Just like everybody else you see, all of these guys are exactly the same. The only thing that makes them all different are the shape nodes they carry up underneath them. How many shape nodes does group 1 have? Group 1 does not have a shape node. All he is a free-floating transform node. He, of course, can be parented into hierarchies. I can middle-click group 1 and make him a child of, let's say, NURB sphere 3. And look at that. A little more interesting of a hierarchy there. Root, child of root. NURB sphere 3 has a child, group 1. Group 1 has 2 children, NURB sphere 4 and NURB sphere 2. Let's go ahead and middle-click group 1 and drag them back out. But I just wanted to show you that with that transform node, we could group them in. So what does a group actually do? It takes your selected transform nodes, and it makes a new transform node and parents your selected ones to it. Okay, let's go ahead and jump back over to the whiteboard. So you're going to need to be able to create groups. So let's see, outside of creation, what else are we going to need to be able to do? We're going to need to be able to parent nodes. You're going to need to be able to rename nodes. Delete nodes. You're going to need to be able to get a list of the hierarchy since we don't have a hypergraph at the moment that we can open up and visualize what the hierarchy looks like. So you're going to need to be able to get a list of all nodes. So list the hierarchy. And since we're dealing with a very simple console screen, we're going to also, let me pull this down just a little bit, we're also going to need to be able to clear our screen. And finally, exit out. All right, good stuff. Now, with this, let's go ahead and start talking about a bunch of rules. So in creating nodes, okay, first of all, I know right now you're probably watching this video and starting to panic a lot. Don't panic. All you're going to be doing is creating nodes. Think all the way back to the Hyperion project in Volume 1. You created rooms. You created items, and you put those items in rooms. Aren't you kind of creating a hierarchy at that point?
Then you took rooms and put those in a level.
And you put those in a level. Exactly. So you have seen a lot of this stuff. When I say you're going to create a transform node, what are you really doing? You're creating an instantiation of a transform node class. And now you've got an object, which we're calling a transform node. It's that simple. So don't panic. I can feel it. I might be 3,000 miles away from you right now, but I can feel the panic. Okay. So let's talk about these rules. So I think for these, Logan, I might go ahead and bring up a new page, because I do believe these are going to be important. Let's go ahead and scroll all the way up to the top without hitting that. Let me clear off a little bit of room here, guys. All right, so all the way up at the top. We shall start off with creating nodes. All right. In creating nodes, all transform nodes are created at the root scene. So all TXFRM, so all transform, me quick abbreviating, okay? Created at the scene root. Okay? Next thing, creating a shape node will automatically generate an associated transform node. So creating a shape node, this is very important. Auto generates an associated transform node.
Just like in Maya when you were creating a sphere. The idea was kind of to make the sphere shape.
Exactly.
But when you created that, you got a transform node that went along with it. That allowed you to position in the scene.
Exactly. Shape nodes are only created as spheres and lights in the program that we're creating now. But it should be easy to extend it such that we suddenly have all sorts of things, boxes, cubes, whatever you can think of. So right now we're just looking at shape nodes as lights and spheres. So spheres and lights. Okay, so that's creating nodes. Now let's take a look at name rules. All right, with our name rules, every node must have a unique name. So our name must be unique. This is very important. You cannot have two nodes with the same name, so your code will have to make sure of that.
Right, it's important because the name is going to be the unique identifier for that node. And later, if you're looking at some of the commands or things that we must be able to do, we have to parent, rename, and delete. You're going to have to be able to specify nodes to use commands like that.
That's right.
And we're going to use the name as that identifier. If you had multiple name or two nodes with the same name, you'd run into a problem because now you would either apply the same thing to the same node or have a node that is inaccessible.
Exactly. All right, so now name assignment must be verified safe before name is assigned.
And this is how we're going to accomplish that. When we try to specify a name, we're going to have a validation process for that name. So depending on how the name is being put together, it will either be adjusted to be unique, or if it's a specific naming command, will simply fail out without renaming, so that you avoid a duplicate naming scenario.
Exactly. So I'll just put must be verified. All right, if a name is taken, then a number is automatically appended.
So again, just going back to what I was saying with autocorrection, in this case, there's going to be two ways that things get named. Either they get names because they were created without one, like we were doing in Maya. Everything that we created, we were just saying, like, clicking the sphere button. We weren't specifying any textual name. So the sphere was getting a name auto-assigned. And you saw as we created multiple spheres, we had sphere 2 and then sphere 3. So it just kept adding numbers to the name as we added more and more objects. So we want to have a scenario set up to where if a name something is attempted to be created, for example, a NURB sphere was attempted to be created, but one already existed, so we'll append 2. If that was taken, we'll append 3, and so on.
Exactly. Okay, next, hierarchy rules. All right, what do we have in the hierarchy? Transform nodes that do not have a parent are considered to be at the root. So the scene's root, if you will. So transform nodes with no parent are at the root. I mean, where else would they be?
Right, they either disappear into the void, or they're all kind of laying out on the table at the root of the scene.
Exactly. Now, transform nodes cannot be parented to any ascendant nodes.
Well, this would get into a scenario where if you have, like we were talking about when you were first drawing out nodes and drawing out the concept of the acyclic graph, the idea that you have a parent, and that parent can have children. All the children then refer to that node as their parent. You cannot run into a scenario where you take the parent node and try to parent it to one of its children, because then if you tried to walk forward through the graph, you would see that you're at node 1, which is the parent. Then you get to node 2, which is the child. If node 1 could be parented to node 2, you would continue walking onto node 1 and node 2 in a loop.
Exactly.
So we need to put in a rule that will not allow the engine to take a parent node and allow it to be parented to any of its children, because that would be either, depending on the scenario, either drop that branch off into space, into the void, or it would create a cyclic condition.
Next, transform nodes cannot be parented to shape nodes.
Right, because the way we're going to handle this is the transform nodes are the actual pieces of the hierarchy. The hierarchy is made out of transform nodes. Shape nodes are simply associated with or connected to transform nodes. So we're not going to build hierarchies out of shape nodes. As a matter of fact, we're going to make sure that nothing can be parented to shape nodes and that nothing can descend from shape nodes. So shape nodes don't have a list of children. A shape node is just a node that is associated with a transform node. Then these transform nodes are what form the actual hierarchy of the scene.
Exactly. Transform nodes can be reparented on the fly.
Well, that's how you would work in this application. Once you've assembled a hierarchy, you might want to move things around to adjust. Otherwise, you'd be stuck with recreating entire hierarchies. This is just a simple editing ability, and shouldn't really be too hard to put together if everything is, well, put together properly.
Right.
The idea is that we can simply take any child, just like in Maya. Take a child and reparent it to some other parent node, or even drop it back off at the scene level.
Okay. So shape nodes cannot be reparented.
Right, that's just going to be a limitation of the way this works, because the shape nodes, they need a transform node to exist anyway. And to move them between the transform nodes wouldn't make sense in this case, because if you wanted to perform that operation, simply take the transform node that shape belongs to and move it in the hierarchy instead. This just goes along with the fact that shape nodes, they create shapes. They're parented using transform nodes, so they can't be moved around within the transform network.
Okay. And this next thing, of course, goes without saying, but you can reiterate on it, Logan, and that is shape nodes always go along with their associated transform node.
Right. They once that association is made with the transform node, that's just basically the node it belongs to. If a shape node needs to know where it is in the world, it looks at its transform node. And as the transform nodes, that basically alleviates any type of positioning responsibility on the shape node. The shape node's job is just to define a shape, define something like a sphere or a light. And they simply basically stay attached to their transform node that they belong to. And we will, of course, need to have facilities to be able to find what is the shape node that belongs to the transform node and vice versa.
Precisely. All right. Almost done. Next, and important, deletion.
Now, just like with working with any kind of scene, we may need to delete nodes after they're created in order to clean things up or just change the scene around. So we need to have any necessary systems in place to allow us to properly and cleanly remove things from the hierarchy.
That's right. And here's a couple interesting rules. When a transform node is deleted, all children nodes are deleted as well.
Because otherwise you would end up with children that would just be, once again, floating around in the void. And also that follows the parenting behavior, since the children in essence belong to the parent. If a parent is deleted, it is as though that entire branch of the hierarchy is erased. This is opposed to a scenario where if you delete a middle node out of a branch and simply break the branch and leave the children around, that would be one theoretical approach. In our approach, we're going to follow the Maya scene graph, and that is, if a transform is deleted, then that entire branch, starting at that node and all of its descendants, or going through all of its descendants, are removed.
And we can prove this real quick by hopping back over into Maya. And let's see, if I was to take this guy and put him up under there, and this guy, put him up under there as well. So we've got group 1, transform node, and it has 2 children, NURB Sphere 4 and NURB Sphere 2. NURB Sphere 4 has 2 children, and it is NURB Sphere 3 and NURB Sphere 1, these 2 guys, him and him. Let's go ahead and put one more under there as well, so the light. Maybe, that looks pretty good. So this guy has 2 children, but one of his children has his own child. If I was to come up here and delete NURB Sphere 4, I will kill everybody on that branch, everybody that's involved in this part of the hierarchy. So we'll select them, hit the delete key, and all gone. All we're left with is group 1 and NURB Sphere 2 because we just deleted that large branch. Okay? So, very important to understand, and so we'll make sure that we follow that rule. Okay, next is when a transform node is deleted, so is its associated shape node.
That only makes sense. And again, if we were to look back in Maya, we'd see that all the physical shapes and lights in the scene that were part of that branch would now be gone.
That's right.
And again, that only makes sense because a shape node has nowhere to exist in the scene if it doesn't have a transform node to tell it where it's at. So we're going to follow the same mentality as with the hierarchical deleting, and that is, along with the hierarchy of that branch, the shape nodes themselves are also removed. So basically, deleting any parent will wipe out that entire branch, shapes included.
Okay, renaming, as I think that's pretty good for deletion. So what do we want to add in here for renaming? Well, when renaming a node, the new name must be verified to be valid before it can actually be applied as the object's new name.
So what would be a valid name? It'd be any name that doesn't already exist within the scene. Because that's what we're defining. The key thing for a valid name is that it be a unique identifier, as in a name that doesn't exist anywhere else in the scene. So if we were to give ourselves a renaming command, we need to make sure that that renaming command would properly check the new name that is being entered and make sure that it is allowed in the scene.
Okay, very good. So final thing I wanted to talk about is command line interface. Alrighty. What is the command line interface? Let's go ahead and jump back over into Maya and take a look at their command line interface. We're going to take this a little bit further. Instead of just having you, through code, create a series of nodes and parent them together, etc., we're going to have you create a command line interface that will allow input from a user so that you can test this out, or you can have your buddy test out your engine, your scene graph engine, by having them simply sit down and create a sphere. As a matter of fact, let's go ahead and delete out this object here. So we have nothing in our scene hierarchy. And we have nothing back here in the world either. So let's go ahead and just kind of...
That again proves the point about shape nodes. There's no shape nodes left to draw on the scene. They've all been deleted.
Exactly. And we can prove that. One, the scene's empty, but if I come back up here to Options, Display, and turn on Shape Nodes...
There's no shape nodes.
There's still no shape nodes. Okay. So, we'll come down here to the bottom right-hand corner and click on this button right here. To bring up the Script Editor. Script Editor is divided up into 2 panes. We have our History pane and our Input pane. From inside the Input pane, I can enter commands. Let's enter a very simple command. I'm going to enter Sphere. Now I'm going to hit Control-Enter to execute this. But when I do, watch what happens. I'm going to give you as much room as possible. So there, and there. So we can see everything. So sphere, Control, Enter. Boom. Everybody comes alive. We have a NURB sphere that's been created at the center of the world. We also have its transform node being shown up here. Not only do we have that, but we also have its associated shape node that was created as well. Because once again, this is where our geometry is. Let's go ahead and turn this back off. All right, very good. So I was able to come down here and simply type in sphere, and, well, we've got a sphere. Now let's go ahead and create, actually I'm going to rename this. So this will end up being another thing that we're going to need to do, as we've already talked about the naming of our node, so watch very carefully. Rename NURBS sphere 1 with a new name. I'm going to call it ball. So here is a case where I am typing in a command, rename NURBS sphere 1, and then I'm telling it the new name is going to be ball. Now, Control Enter. Look what happened. Ball. Very good. So a simple command. I think we'll have to add that command to the list of commands accepted by your command line interface. Very nice. Now with ball, let's go ahead and create a new ball. So if I was to come up here, edit, and we can just duplicate them, move them on over a little bit. So now we've got ball and ball 1. We could add duplication too in there. No, we won't do that, but easily we could. But so we've got ball 1 now. So we've seen how we can do renaming. We can do groups with commands. So if I wanted to group, G-R-O-U-P, space, ball and ball 1. So group ball and ball 1 and select Control Enter. Ball and ball 1 have been parented to a new transform node that has been added to the scene called group 1. It's as simple as that. I can still unparent these guys. Okay. Now I just have a transform node just hanging out there. Let's come up here to Options, Display, and turn on Shape Nodes. It's just a transform node. He has no associated shape node. You're going to need to be able to create the same scenario in your application. Let's go ahead and come back up here once again. I know I've turned this on about 100 times. Let's go ahead and turn it back off for the 100th time. Okay, so as we work our way through this, so parenting. If I wanted to be able to parent, actually, let's not type in there. That's not a good idea. Let's type down here where we're supposed to. Parent. Who do we want to parent? I want to parent ball 2, ball 1. So once again, a command, and then who I want to parent it to. Control, Enter. Ball has been parented to ball 1. Then if I wanted to take ball 1 and parent it to group 1, I could simply say parent ball 1 space, for you could just out loud say 2. So parent ball 1 to group 1. Bam. There you go. So this small part of the hierarchy has just been parented into group 1. So group 1 is our only root level transform node. All right, very good. So that's a little bit of grouping action. That's some parenting action. That's a little bit of renaming action. Now, obviously, we're going to need some means of seeing the hierarchies that are going to exist in your memory. Here, with Maya, we have the convenience of the hypergraph. Now, of course, it will be a breeze for us to write our own hypergraph to show the exact same kind of information a little bit later in time. But right now, you guys haven't done much work with graphics, so it's just going to be a simple console application, though your engine needs to be designed in such a way that we can easily use it in, let's say, our own 3D application that we write, or even 2D application that we write. But in the console app, we need some sort of rendering engine, if you will, and what we're going to do is have you create a simple command called ls, and ls will get you a list. So in this particular case, I'm just going to select 3 objects, and I'm going to go a little bit above and beyond what you're going to have in our application. I'm going to say ls for list dash sl, meaning show me selected. Execute, and the result, if we look up here in the history pane, is group 1, ball 1, and ball. Okay, so we got a list of our 3 objects. Of course, we can't see what the hierarchy actually looks like with them. We have to look up here in our hypergraph to get an idea. When you list them out, I want to be able to see what the hierarchy looks like. You should be able to see. And we'll take a look at that in just a few minutes over on the whiteboard. Okay, so now that we have an idea of being able to come in here and type in commands, let's turn our attention back over to the whiteboard. Let's go ahead and bring up a new sheet of paper real quick. So new whiteboard. Hide this one. And let's scroll back up. All right. So in regards to commands, the first thing I want to do is take a look at command line interface. All right, on the command line interface, the very first thing is case sensitivity. It needs to be case sensitive. If you think about it, well, if you knew Maya, you'd know real quick it's case sensitive. So I'm not going to go back over there. I'm just going to say it needs to be case sensitive. So let's jot that in. Next, the enter key will execute whatever command you've typed in on the line. Next, the command must be a valid command, obviously. Which brings up a very interesting question. What are our commands? The following commands need to be implemented in your application. So here's our command list. We have, starting with ls and an optional node. Come back to this in just a minute. Clear. Just in case your screen is getting a little boggled with a whole bunch of text, you can clear it. Sphere. And an optional name. Light. And an optional name. Parent. And then some required names. Simply come in here and give it node 1, which node 1 is going to be a child. So I'll just do node 1 and node 2, then I'll explain.
Maybe you can just point it out and diagram it after.
Yep.
Because as far as the syntax is concerned, those are just two arbitrary nodes.
They are, because there is no parent-child relationship at the moment. That's the idea. All right, unparent. Rename. And rename is going to take in an old name. And your new name. Delete. I'll simply take in a name, so I can say delete ball, and it'll delete the ball. And finally, exit. All right, so utilizing everything that we have over there, let us go ahead and just walk through some very simple node creation. We'll simulate it here on the whiteboard and then show you what kind of results we get by using things like the list command, parent command, etc. So when we start off, we need to have some sort of prompt indicating that we can type. What I want you to have is a simple colon. Okay, so you have a little flashing cursor right there. So you're ready to type. So if I was to start out by doing an ls and hit enter, you'll notice providing a node name is optional. So if I do ls and enter, nothing's going to show up. We'll just end up with another colon down here and a flashing cursor waiting for us to type, because currently we have no nodes in the hierarchy. So let's start out by creating a sphere. So what we need to get now, if we were to turn around and do ls, we would see sphere, and then in brackets, sphere shape. This is an actual node. It needs to be an actual node.
A shape node.
A shape node, that's right. And this is an actual node. This needs to be a transform node. But this is what we would get at the moment. Now let's create another sphere. No, let's create a light. And hit enter. If we were then to turn around and type ls, we would then see the same sphere line that we've got, and we would also see light, and then inside square brackets. Now this isn't optional. This is what's being echoed out to your viewport or your console window. So light, shape. So it would be on the light shape, we'd find things like the color of the light, the intensity, etc. So far, so good. Now, the next line, or the next time I entered a command in, let's say I did something along the lines of parent, I don't know, how about the sphere to the light. Because obviously I can't take the sphere and parent it to its shape node or the light shape node, because as we said a few minutes ago in our rules, you cannot parent transform nodes to shape nodes. Nothing can be parented to a shape node. So if I was to do ls after this, what would be echoed out would be the following.
Depends on how closely you read into the syntax. One of the requirements is that the command line be case sensitive. And just the way you happen to have written both those names, light and... oh no, I just tripped myself up my own logic. You didn't specify a name for light.
Right.
That's where you're going now.
Yeah, so it just gave us light. Alright, so now when this draws out, it needs to look like this. Notice how we've thrown in the two dashes there. It just indicates that sphere is a child of light. It's just our way of getting a visual representation of the hierarchy that is being created.
And that is to simply indent
That's
every time
indent.
something is the child of basically the line above it, if you want to look at it that way, because each line is going to print out exactly one transform/shape pair. You're never going to have a case where you have lots of transform nodes all on the same line. So basically, line by line, you should print out a transform node and its related shape node. And then below that, if there happens to be any kind of parenting in place, indicate that by offsetting and applying dashes, so that we could see that if light was followed by sphere and sphere was indented, that means that sphere is a parent of light. Sphere is a child of light.
That's right.
Not parent. Other way around.
Okay, so now let's say I came in here and I typed in sphere again. And then I gave it the optional name, ball, and hit enter. Because remember, sphere can optionally have a name for it. And then let's say I turned right around and on the next command I typed in parent ball to sphere. Case sensitive, so ball little to match the name that I gave it, little case B, sphere with a capital S to match the capital S being used in its name. Now if I was to do an ls, I would see exactly what I've got drawn down here at the moment with this added in. Notice the naming. Notice how the shape node is actually called ball shape. Keep that in mind when the shape node gets created. Very important. But I can see by the hierarchy that's being drawn out now that light is at the root. Sphere is parented to light, is a child of light, and ball is a child of sphere. So if I turned around and created one more sphere, with the way and then did an ls, with the way we've got this set up, what we would see now would be light with a child sphere, with it having a child sphere ball, with it having a child called ball. And then finally, we would have sphere 2. So instead of starting at sphere 1, we just call it sphere. Or instead of starting at light 1, we just call it light. The very next one's going to start at 2, though. So we've got sphere, then sphere 2, sphere 3, sphere 4. So this one, since we did not specify a name, it automatically got the name 2. Okay, so sphere 2. All right, so there you go. Now, of course, I could turn right back around. Let's pretend we are still doing commands all the way up here. And I did something like rename sphere shape to X. Well, what would happen would be sphere shape just turned into X, like such. So with rename, I can rename shape nodes, I can rename transform nodes. You just need to make sure that node exists and that the name you want to name it to is a valid name. And that's pretty much it. So this is the goal of the application that you need to write. You need to make sure you use object-oriented programming for your nodes. This is very important. Think about what all of your nodes have in common. Use inheritance. This is important. Right now, we've got a light and a sphere that represent shape nodes. As a matter of fact, they both, you could say, extend shape node to give it perhaps geometry for the sphere and an actual light for the light. So you have to think about it and plan this out. There's obviously going to be a loop in there that's going to work with your command line interface so that you can keep typing commands in. Now, this is the objective of this knowledge review. This is not meant to be a 5-minute knowledge review. Please keep that in mind. This is supposed to be challenging. Now, if you are completely panicking at the moment, you know with knowledge reviews, we always show you the answer. So you feel free to go off and try to tackle this application. Do the best you can. Then come back and watch the videos that we release showing you how to put this together, but we're going to show you how to put it together in stages so that you can watch, oh, I just got a hint from you. Maybe I can go back to it and get a little bit closer. Or, the hint didn't work. Let me watch how you actually did this part. Okay, that makes sense. And perhaps that might work as inspiration for you to finish the rest of it. Who knows? It might be just the thing to get you going on figuring out how the rest of it needs to flow. I do highly recommend sitting down with a piece of paper and a pen, as I said at the beginning, and drawing this out first. Planning this application is extremely important. So, to wrap it all up, are we asking you to create a scene graph as found in Maya? Answer, yes. Are we asking you to create something similar to Mel? Well, yeah, kind of. But you have all of this knowledge. You just need to get in touch with it and figure out how to put it together in such a way that you can achieve a program that does this. So that is your challenge. So rewatch the video if any of this seems confusing. Everything has been spec'd out on the whiteboard. And then pick back up with the next video and start watching how we do this. So with that, best of luck. Please don't just give up without even getting started. Go ahead and give it a shot. And we will see you very soon. So thanks a lot.